For months, humanity's most distant spacecraft was talking to us, and every single word coming back made no sense at all. Not silence, not static. Something far stranger, a steady stream of data, perfectly formatted, arriving right on schedule that simply didn't mean anything. Engineers on a team built specifically for a machine older than most of them had to figure out what had gone wrong, using nothing but patience, decades-old blueprints, and a signal that takes almost a full day just to reach them. What they eventually found wasn't a broken part in the way anyone expected. It was something closer to memory loss, and fixing it meant solving a problem nobody had ever solved at this distance before. It's worth taking a moment to appreciate exactly what kind of mission the spacecraft was originally built for, because the scale of its actual achievements tends to get flattened by how familiar the name has become over the decades. Voyager 1 wasn't originally designed to become the most distant human-made object in existence. That was never the primary goal written into its earliest mission plans. It was built to take advantage of a rare planetary alignment, one that happens only once every 176 years, allowing a single spacecraft to visit multiple outer planets using a sequence of gravitational slingshots instead of burning through impossible amounts of fuel. It delivered stunning, detailed images of Jupiter and Saturn that redefined how scientists understood the outer solar system almost overnight, revealing active volcanic activity, complex ring structures, and moons far stranger than anyone had previously modeled from ground-based telescopes. Once that primary mission wrapped up, engineers made a decision that, in hindsight, turned out to be one of the most consequential choices in the entire history of space exploration. Rather than simply letting the spacecraft go silent once its main objectives were complete, they kept it running, extending its mission indefinitely, transforming a planetary tour into something closer to an open-ended journey toward the edge of everything we understand about our own solar system. That decision is exactly why, decades later, a small dedicated team is still carefully maintaining a computer system built using 1970s engineering, patiently working through problems nobody could have specifically anticipated when the spacecraft first launched. To understand why this glitch was so unsettling, you need to understand exactly how Voyager 1 talks to Earth in the first place, because it isn't simple, and it's never been simple. One of those systems is responsible for taking readings from every instrument still functioning on the spacecraft, packaging that information into a readable, structured format, and sending it back to Earth in a steady, predictable stream, the same basic process it's followed reliably for nearly 5 decades. Voyager 1 carries its own golden record, an actual physical time capsule bolted to its exterior, etched with instructions, filled with sounds and images meant to represent the full breadth of human culture and biology, on the small chance that something someday encounters it drifting silently through interstellar space. That detail transforms Voyager 1 from a purely scientific instrument into something closer to a message, a deliberate physical piece of humanity sent outward with no expectation of ever being found, let alone understood, by whoever or whatever might eventually come across it. Which makes the stakes of any serious technical failure feel different than they would on an ordinary scientific mission. Losing contact with Voyager 1 wouldn't just mean losing a stream of scientific data, it would mean losing our last active line of communication with a physical artifact that will likely keep drifting through the galaxy for millions of years after every trace of the civilization that built it has vanished from Earth. That weight sat quietly in the background throughout the entire months-long effort to fix the garbled data problem, even though nobody on the engineering team needed to say it out loud during their daily technical briefings. Here's what made this particular failure so strange, and so different from every other issue the mission had faced across its entire history. When a spacecraft breaks in a conventional sense, it usually goes quiet, or it sends back an obvious error code, something engineers can immediately recognize and start troubleshooting right away. This wasn't that, and it took the team time just to understand what kind of problem they were actually looking at. Voyager 1, I can be sailed on matters. Voice 1 kept transmitting a perfectly steady signal, right on its normal schedule, formatted exactly the way engineers expected it to be formatted. But when they tried to decode it, the numbers were meaningless, a repeating pattern that didn't correspond to any known instrument reading, any status update, any piece of telemetry the team could recognize from decades of familiarity with this exact spacecraft. It was, in a strange way, like receiving a letter written in your own native alphabet, perfectly spaced and punctuated, every letter formed correctly, that turned out to be complete gibberish the moment you actually tried to read it and make sense of the words. For months, the team couldn't get a clear picture of the spacecraft's health at all. They didn't know if its instruments were still working properly. They didn't know if it was correctly pointing its antenna at Earth. They had a working transmitter, faithfully sending signals home, and nothing genuinely useful coming through it. And every single test they wanted to run came with the same brutal, unavoidable cost. Send a command, then wait nearly 2 full days for any kind of response, then spend additional time carefully analyzing whatever came back before they could even plan the next logical step in the investigation. That kind of pace, so painfully slow by any normal engineering standard, meant a diagnostic process that might take an afternoon on a spacecraft closer to home, instead stretched out across weeks and eventually months of careful, deliberate work. It's worth imagining for a moment what those months of uncertainty actually felt like for the people living through them day to day, rather than simply reading about the technical details after the fact. Every morning, team members would arrive expecting the possibility that the next scheduled communication window might finally bring back something useful, only to spend another day analyzing the same meaningless pattern of numbers that had shown up the day before and the day before that. There was no guarantee the problem was even solvable. For all anyone knew in those early weeks, the spacecraft's flight computer could have suffered damage severe enough that no amount of clever remote reprogramming would ever bring back readable telemetry again. That uncertainty carried real weight, given exactly what losing this specific spacecraft would actually mean. Voyager 1, Voyager 1 isn't a mission that can simply be relaunched or replaced. There is no backup spacecraft sitting in storage somewhere, ready to take over if this one goes permanently silent. Whatever science it's still capable of gathering exists nowhere else, collected by no other instrument humanity has ever built or sent this far from home. Some engineers on the team have spoken about approaching each new diagnostic step with a kind of deliberate, disciplined patience, treating the problem less like a race against time and more like a careful, methodical puzzle that simply had to be solved correctly, no matter how long it ultimately took to get there. That mindset matters more than it might initially sound like it should. Rushing a fix at this distance, in an attempt to save time, would have carried real risk of making the underlying problem permanently worse, given how little room for error exists once a single flawed command is sent nearly 15 billion miles into deep space. The deeper the team dug into the problem, the stranger it became, and the more it started to look like something well outside the range of failures anyone had specifically planned for. Eventually, engineers traced the garbled signal back to a single onboard computer, responsible for organizing science and engineering data before it gets transmitted home to Earth. Inside that specific computer, they suspected, a single chip had likely stopped working correctly after decades of continuous operation in one of the harshest environments imaginable. Here's the part that made this feel almost impossible to solve using any conventional approach. That chip didn't just process data as it passed through the system, it also held a small piece of that computer's own operating code, instructions the system needed simply to function correctly on a basic level. When it failed, the computer wasn't just producing bad output anymore, it had effectively lost part of its own memory, a piece of itself it needed just to keep functioning normally, buried somewhere inside hardware that had been running continuously since before most of the current engineering team was even born. For any spacecraft built in the modern era, that kind of failure usually has a relatively straightforward fix available. Reload the missing code from a backup copy stored elsewhere in the system, and move on with minimal disruption. But Voyager 1 doesn't have room for a simple backup like that, not in the way modern engineers would normally expect. There was no replacement chip sitting in reserve. There was no way to physically swap anything out, obviously, on a spacecraft sitting over 15 billion miles away from the nearest engineer. And there wasn't enough spare memory anywhere else on the computer to simply copy the lost code back into its original intended location. So the team had to do something that sounds almost absurd once you actually say it out loud in plain language. They decided to rewrite the spacecraft's own code, live, from Earth, and scatter the pieces across whatever unused memory they could find, scattered elsewhere in the system, all while the spacecraft itself continued moving, continued operating, continued sitting over 22 light hours away from anyone capable of fixing it directly. Solving a problem like that meant going back to documentation written decades earlier by engineers who, in many cases, had long since retired from the space program or passed away entirely, studying code written for a computer architecture that stopped being taught in most university programs before the current team members were even born. Some of that documentation existed only on paper, stored in physical archives rather than digital files, requiring team members to track down printed technical manuals from the 1970s just to understand exactly how the original system had been designed to function in the first place. Younger engineers on the team, some of whom had joined the mission specifically because of a fascination with exactly this kind of vintage engineering challenge, spent weeks essentially teaching themselves a programming language and hardware architecture that had been effectively obsolete for most of their own lifetimes. The team split the affected code into smaller, more manageable sections, small enough to fit into scattered, unused corners of the computer's remaining working memory. Then carefully rewrote the instructions so each individual piece would still function correctly, even though it was no longer stored anywhere close to where the original system architecture expected to find it. Every single change had to be planned with extreme precision before anything was ever transmitted, because there was genuinely no room for casual trial and error at this distance. A single careless mistake risked making the spacecraft's telemetry even less recoverable than it already was, or worse, risked permanently damaging the fragile channel of communication with a machine. Humanity has absolutely no way of physically reaching, ever, under any conceivable circumstances. They started deliberately small, sending a modified piece of code covering just one specific part of the affected system first, a low-risk test designed to confirm the basic approach would actually work before committing to anything larger or more ambitious. Then came the wait. Nearly 2 full days passed before any response could possibly arrive, an agonizing stretch of time for a team that had already been working the problem for months without a clear resolution in sight. When the response finally did arrive, it worked. For the first time in months, meaningful telemetry, genuine, readable information about the spacecraft's actual health and status, arrived back on Earth, decoded successfully, confirming the basic repair strategy was actually functioning as intended. There's something worth pausing on here in terms of what that first successful signal must have actually felt like inside the control room. Months of uncertainty, months of not knowing whether the spacecraft's instruments were even intact, suddenly resolved by a short, successful stream of ordinary, boring, perfectly readable numbers. From there, the team methodically repeated the same painstaking process for the remaining sections of the affected code, working through the repair section by section, patiently completing something that would have taken minutes on almost any modern computer sitting on a desk here on Earth, but instead stretched out across additional weeks, purely because of the sheer physical distance involved in every single exchange. Each successful step brought back a little more of the spacecraft's full diagnostic picture, gradually restoring the team's ability to actually monitor Voyager 1's health in real detail, rather than simply hoping everything on board remained in working order. What makes this story remarkable isn't just that the fix eventually worked. It's what the fix actually proves about a spacecraft that's now nearly 50 years old, operating in an environment nobody who originally built it could have fully anticipated. Voyager 1 wasn't designed with this specific kind of repair in mind, because nobody in 1977 could have reasonably planned for a team. Decades later, essentially performing delicate surgery on the spacecraft's own memory from over 15 billion miles away, using nothing but patient trial and error and documentation written before most of the engineers involved were even born. And yet it worked. Full, meaningful science data began flowing again, confirming that the spacecraft's remaining active instruments, still functioning after all these decades in the harsh environment of interstellar space, were continuing to gather real, valuable information from a region no other human-made object has ever physically traveled through before or since. It's also a quiet, understated reminder of exactly how much institutional knowledge it genuinely takes to keep a mission like this alive, decade after decade, long after the original engineering team has largely moved on or retired. Every successful fix depends entirely on engineers willing to study technology most of the modern world has long since forgotten, simply because the spacecraft carrying humanity's furthest physical reach into the cosmos still depends completely on systems designed in an entirely different technological era. That dependency creates a strange kind of responsibility that doesn't really exist anywhere else in modern engineering. There's no updated hardware waiting in the wings to eventually replace this specific machine. There's no newer version quietly picking up the slack somewhere nearby. Whatever knowledge keeps Voyager 1 running has to survive, generation after generation of engineers, purely through careful documentation and deliberate teaching. It's worth remembering, too, that this wasn't the mission's first brush with a serious, potentially fatal technical problem, even if it was one of the strangest. Over nearly 5 decades of continuous operation, engineers have had to work around failing instruments, dwindling power reserves, and computer systems slowly showing their age in ways nobody could have fully predicted at launch. Each time, the same basic pattern has repeated itself. Patient diagnosis, careful planning, and a willingness to solve problems using methods that would sound almost unreasonably difficult on any newer spacecraft. What sets this particular repair apart is the sheer conceptual strangeness of the underlying problem. This wasn't a failing sensor, or a stuck valve, or a slowly draining battery, the kinds of failures engineers have well-established playbooks for handling. This was closer to a form of digital amnesia, a computer that could still technically function, but had quietly lost part of its own understanding of how to communicate clearly, requiring a solution that looked less like conventional spacecraft repair and more like a form of very careful, very patient computer archaeology. There's a particular kind of satisfaction among the people who work closely with this mission in solving a problem that genuinely has no modern precedent to draw from. No manual exists for fixing a 50-year-old spacecraft's corrupted memory from 15 billion miles away, because nobody has ever needed to write one before. Every step of this specific repair effectively became its own precedent, documented carefully along the way, not just to fix the immediate problem, but to leave behind exactly the kind of knowledge some future engineer working on the same aging spacecraft years from now will very likely need to draw on again. That's part of what makes Voyager 1's continued survival feel less like a static historical artifact quietly drifting through space, and more like an ongoing living relationship between a machine built in one era and a team of engineers constantly adapting new solutions to keep that same machine talking clearly across an ever-growing gulf of both distance and time. There's a broader lesson quietly buried inside this entire story, one that extends well beyond a single spacecraft or a single stretch of garbled telemetry. Every piece of technology humanity has ever sent beyond Earth eventually faces some version of this same fundamental challenge, the slow, inevitable aging of hardware that can never be physically repaired or upgraded once it leaves the ground. Most missions never get the chance to demonstrate just how far patient, creative engineering can actually stretch that lifespan, simply because most missions don't survive nearly as long or travel nearly as far as this one already has. Voyager 1 has become something close to a living case study in exactly how much life can still be coaxed out of aging hardware, given enough patience, enough institutional memory, and enough willingness to solve problems using methods nobody originally planned for at launch. That's arguably the most valuable, least talked about legacy of this entire mission, separate from any single scientific discovery it's made along the way. It's proof, updated and reinforced every time a new problem gets solved, that careful patient engineering can meaningfully outlast the original expectations placed on a piece of hardware by decades, sometimes by half a century or more. Voyager 1 spent months speaking to us in a language that looked entirely familiar, but meant nothing at all, and the eventual fix wasn't a repair in any conventional engineering sense. It was closer to relearning how to speak clearly again, one carefully rewritten fragment of code at a time, across a communication gap of over 15 billion miles, using nothing but patience, decades-old documentation, and a willingness to try something that had genuinely never been attempted before at this kind of distance. It's a strange, quiet kind of resilience worth sitting with for a moment. A machine built entirely with technology from another era, kept alive not by newer replacement hardware, because none exists or ever will, but by people patient enough to meet it carefully on its own terms, using tools and knowledge that mostly disappeared from everyday use decades ago. Every additional year, Voyager 1 continues transmitting is, in a very real sense, borrowed time, made possible only by a small, dedicated team willing to relearn forgotten skills, specifically to keep one aging spacecraft talking just a little bit longer. And somewhere out there, well beyond the edge of our solar system, that same spacecraft keeps drifting further from home with every second, carrying instruments, still quietly gathering real scientific data from a region of space nothing else humanity has ever built has come close to reaching. If you want to see exactly what Voyager 1 is still discovering now that its voice has been fully restored, that's exactly what I'll be covering in detail in the next video. Subscribe so you don't miss it when it goes up. And before you go, tell me in the comments, what do you think finally silences Voyager 1 for good, a future fix nobody manages to find in time, or simply running out of power to keep listening to us at all? I'll be reading through the answers, and I'll pin the one I think makes the most interesting case.